All right, everybody, welcome to lesson 10, the last one in our series on quadratics, where we'll put everything together and deal with the word problems, which is like the bane of everyone's existence. For whatever reason, the word problems cause a challenge because they really don't tell you what to do, right? They really don't tell you how to approach something. So they are a struggle because we have to put together all of the things we learned in quadratics and be able to interpret all of the things we're told, which is a challenge for a lot of people. But there's a basic kind of structure and format which we can follow every time, which, with practice, things do get better. So the more that you try, the more variety of things that you see, the better equipped you are to deal with, maybe a quiz coming up for you, an exam, something like that. So we'll do a few here, different types of questions, and hopefully that helps you get ready for whatever it is you may have coming up. So let's just talk about the top part here for a second. So just remember that if a quadratic function has a maximum, it means that it opens downwards, right? Because we can follow that parabolic shape around, and if it's a maximum, my end points are going to be pointing down. So if my a value is something that's less than 0, in other words, the coefficient of a is negative, then it will have a maximum because it'll open downwards. Now if it's a minimum, the opposite is true, and this will open upwards. So a needs to be positive for that to happen. And you can think about just drawing yourself two pictures, right? If a is negative, it opens downwards, but if b is positive, well, then it opens upwards. Just a little picture like that. So I've got a minimum if it's positive, a maximum if it's negative. Now that maximum or minimum value comes from our vertex. So if that maximum minimum value it's going to be q when x is actually equal to p. Because if x is actually equal to p, well, this whole first term gets zeroed out, and I'm just really left with my maximum value or minimum value of q. So really the only thing that we care about in every word problem here is going to be the vertex. It'll tell us if we have a maximum or a minimum. The vertex is what's important. Okay, so that's what we're going to try to find. And if you remember all the ways that we found the vertex, well, the main one was us using complete the square. Right, so if I can get it into our standard form by completing the square, I'm going to know what the vertex is. So let's see if we can do that in a variety of situations. So let's apply all the things that we know. So we could have one type here which says I've got a number problem. So for this first example, we're told that two numbers have a difference of 8. Difference is the word in math that means subtract. The problem is I don't know the two numbers. I don't know any relationship between them. I don't know if one number is 10 more than the other. I really have nothing to go off of. So the two numbers right now I have to assume are totally different. So the first number I'm just going to call x. The second number I'm going to call y. Right? Two different variables to define this because I really don't know anything about the numbers. All I know is that if I subtract them, I have to get 8. Now the order you do this subtraction doesn't matter because I don't know what the numbers are. So if I do x minus y is equal to 8, well, that says two numbers differ by 8. Okay, and we're also told to determine those two numbers so their product is a minimum. Their product is a minimum. So the other thing I know is, well, the product means to multiply. The product of two numbers is, well, the multiplication of those two numbers. I just don't know what they are. If this is supposed to be a minimum, again, I should know that my coefficient of a, the value of it, is going to be positive. I don't know what it is necessarily right now, but I know if I have a minimum, my graph will open upwards. So we need to use these two things in step number 2 here to put them together to make one equation. Okay, so what I really can do here is recognize that my product is right now in terms of two variables, x and y. The issue is I need it to be in terms of one variable. So take the original equation you had x minus y equals to 8, write it in terms of one variable. So I either make it say x is equal to everything else, or y is equal to everything else. The one you choose doesn't matter. In the end, we're going to find both numbers anyways. So pick the one that looks easiest to you. So what I'm going to do is take that original equation and solve for one of the letters. Okay, and what I'm going to do is add a y to both sides. So x is going to be equal to y plus 8. Now I have some expression for x that I'm going to use to help me find the product of those two numbers, p for product. So I'm going to take what I know x is and substitute it into that product equation. So now I'm going to know that the product is going to be equal to, well, x is now y plus 8, and I'm going to multiply it by y. I took out x and put in what x was equal to. All I did was make a substitution. But now I can multiply this out and distribute. So you're going to get y squared plus 8y. Now if I look at this right now, usually all of our quadratic functions are in terms of x. It doesn't need to be, the variable is arbitrary. This one is just in terms of y. So I know when I solve this, I'm going to get the value of the second number. That's what we defined as y. Once I have it, I can use it to find the first number, which is x. Now at this point, I don't really see what the vertex is, right? I just have a binomial, y squared plus 8y. So what I'm going to do to find the vertex is complete the square. So my product is going to be equal to y squared plus 8y. Now I have to think about the number I'm going to add, so I can take my 8, right, my number that's in front of my y, divide it by 2, and square it. So 8 divided by 2 is 4, squared is 16. But I also have to remember to take 16 away, because if I don't, then I've just changed the value of this function. Now I can actually write it in our factored form, our vertex form of this. So my product function is equal to y plus 4 squared minus 16. Okay, now I can see what my vertex is. Once you've completed the square, you're going to look for the vertex. Okay, so I'll put this in a box. There's our completed square function. And the vertex from that equation that we got by completing the square, the vertex is minus 4 minus 16. Remember that the number inside that set of brackets attached to your variable, the sign should be backwards. Okay, so now what this tells me is I know that the value for y, the first number or the second number we defined, y has a value of minus 4. Now it looks weird because every coordinate pair you know always started with an x coordinate and then ended with a y coordinate, but we defined things differently in our function. And now we said the input to it, we labeled it as y. So the variables are arbitrary. It doesn't matter what you call them. We called this one y. So I know I solved for my second number because I also called that one y. But that doesn't mean that the other one is now x. That's actually the product of the two numbers, because that was what my function was equal to. So this is the product when the value of the second number is negative 4. My only job now is to find the other number. So originally we said that the product was equal to x times y. My two numbers multiplied together. Well, we just found out that the product is negative 16 and the value for y is negative 4. The only thing I don't know is x, which means that positive 4 has to be x. And well, if I really interpret this, and I'll write us out a statement here. So therefore, the numbers are positive 4 and negative 4. Right? The first and second number, the two numbers I have, positive 4 and negative 4, they differ by 8. If you were to subtract them, you will end up with 8. Right? If x is positive 4 and y is negative 4, x minus negative 4 is 8. Multiply them together and you have your minimum value of negative 16. Okay, so I've satisfied both the conditions I need to. I found both of the numbers. And again, all I really did was complete the square to find it. Once you complete the square, look for the vertex. So we'll try it again. We've changed it up a little bit. So if you want to try it on your own right now, just hit pause and then, continue the video when you think you've got something. But again, we're told two numbers have a difference of 18. So if I define them as the first one is x, the second one is y, if you subtract them, you need to get 18 as your difference. We don't know if the product has a maximum or a minimum right now, but what I do know is I have a product, right? X times y. So I need to take our first equation we got, our difference, write it in terms of one of the variables. So again, I'll do it the other way this time and solve for solve for y. So that if I do x is equal to 18 plus y, that means that x minus 18, is actually what y is equal to. Now I can put that into my product function in replacing what y is this time. And I get x minus 18 is y multiplied by x. So I know my product function has an input value of x where it's equal to x squared minus 18x by distributive property. I also know now that it also has a minimum because my coefficient of my squared term is a positive, so I know this opens upwards. Okay, so now I am going to complete the square again to determine my vertex. So my product has an input of x, so that x squared minus 18x, and I'm going to add 81 this time because if I do 18 divided by 2, I get 9. 9 squared is 81, so I also have to take 81 away. So my product function has a format of x minus 9 squared minus 81. So I know my minimum is at negative 81, and I know my value of x is 9. Right? My vertex has coordinates of 9, negative 81. That vertex really tells me the input, which I used as variable x this time. The output tells me the product when I input x in terms of function notation. So it doesn't tell me the y value, it tells me the minimum product. So if x is 9, well, now I know the other number, and I'll use this first equation to do it. If I know x minus y is 18, we just figured out that 9 is x, the only value that y can be is negative 9 to make this happen. Right, so those two numbers are 18 away from each other, right? They differ by 18, and their product is a minimum value. Right, if you multiply them together, you get the smallest value possible, negative 81. Okay, so same sort of situation, but we solved for the other variable this time so you could see the other way. But really it's identical. It doesn't matter which variable you solve for. The other type of problem we could think about is a maximization problem in terms of area. So it says Ms. Neufeld is making a quadrilateral enclosure for her cat. It's a catio if you don't know that. Kind of like a patio, but like for cats. Using 500 meters of fence. Determine the dimensions with the biggest area possible. Now I don't know if it's a square or a rectangle or some other shape, so let's just assume it's a rectangle for now. If I happen to determine it's a square later, then I can revise the picture, but I shouldn't assume that it's equally split. I really should assume that it's different. Now I know that if it's a rectangle, I'm going to have differing dimensions. So I'm going to have a pair of x's and a pair of y's, right? A pair of lengths are the same, a pair of widths are the same. But in total, I have to use 500 meters of fence. Now that's not the area on the inside. I don't know that. I do know that the 500 is all I have to use to build this, so it's the outside. So I know that if I do 2x plus 2y equal to 500, well, that's my perimeter formula. Add up the four sides, it gets you my total of 500. And I'm trying to determine the biggest area possible. Now the area of a rectangle is length times width, so in other words, x times y. And this is going to look oddly familiar. It's literally the same format we used above for a product. But our product now has a meaning, it just means area. This is the exact same question to what we did above. So pick a variable and solve for it. I'm going to solve for y. So that 2y is equal to 500 minus 2x, and to get y by itself, divide everything by 2. So that y is going to equal to 250 minus x. Okay, now that I've got that, we can plug it into our area formula. So area, in terms of x now, is going to be, well, the x that was already there before, y is going to get replaced, and y is going to become 250 minus x. Because I know that's what it's equal to. That's what we just figured out together. Right? Y is the same thing as 250 minus x, so I can make a substitution. So my area function is actually equal to 250x minus x squared. If I reverse the terms, all I did was switch them around. Now it looks more familiar. Again, we're going to find the vertex, and I can do it by completing the square. So we'll factor out a negative sign first. So x squared minus 250x. And I know that since there's a negative there, I know I have a maximum because this will open downwards. So I know I'm on the right track already. I just need to figure out what to add and subtract. So I'm just going to grab my calculator here. Up. Okay, so now I'm going to take my 250 number, divide it by 2, and then square it, just like we did before. So I'm going to actually add into this set of brackets 15,625. Now, this is where a lot of people get confused. Since I put in 15,625 into the set of brackets and I put in a positive, most people will subtract that number on the other side, right? Which seems like a reasonable thing to do, positive and a negative. But you need to remember there's a coefficient outside this set of brackets that's a negative. Now if I actually distribute it into the brackets to get rid of them, what I actually included here is negative 15,625. The negative on the outside will multiply with it. And if I include a negative of the same number on the outside, well, I've just done the same thing twice. I didn't cancel it out. So I actually have to include the positive one on the outside as well. So it looks like they're both positive, but because there's a negative on the outside that has to get distributed, it actually turns the one inside to a negative number. So you can distribute to C, but really this is what equals 0. So it looks like they're both positive, but they're not. So just be very careful. Now if we go write it in our factored completed square format, we've got negative x minus 125 squared plus 15,625. If I look and determine what the vertex actually is, let's make this a little room here. If I actually look for that vertex now, I know that x has a value of 125, the area is 15,625. Again, that's my x coordinate. That's because my whole function was in terms of x, so that number is x in my picture. The 15,625 is the area when I input x. So I know the maximum area, 15,625 meters squared. I also know that x has a dimension is 125 meters. Okay, so I can go find out the other dimension as well. So if x is equal to 125 meters, there's a couple ways I can go find out what y is. I have a formula highlighted in orange to do it. So I know y is 250 minus x, which is 250 minus 125. So now I know for sure that y is 125 meters as well. So now I actually know that this is a square. I didn't know it when I started. I needed the vertex to do it. Okay, so there's the biggest area possible, 15,625. Dimension of x is 125, and you can find y by using the formula you defined in the first place. Okay, so really the same question. Get one of your variables solved for, substitute it into your area expression, complete the square, look at the vertex, right? They're all very much so the same. The one underneath is again very similar, but the picture may be a little confusing. Okay, so the coach of this volleyball team has 800 meters of rope to enclose the players at a restaurant. They are being restricted to a rectangular section of the restaurant. So I'm just going to draw a rectangle right now. Okay, so we're restricted to a rectangular section that is also divided into 3 smaller sections against the wall. That's key. There's a wall. Now if you imagine this situation, you're not going to need to put rope against the wall as well, because the wall acts as a divider. But I am going to divide this into 3 smaller sections. Right, so there's a section, and that last chunk gets split into 2 parts. So I've got 3 sections here in total. Okay, the part that the rope is actually going to go on is everything that's not the wall. Right, the wall acts as a divider already. Okay, so I'm not going to put rope along the back, but everything highlighted in green is going to get rope to cut it up into parts, to divide it. Determine the dimensions of the rectangle that will maximize the area that they are in. Now when it says the dimensions of the rectangle, we are talking about the large one, not the 3 small ones in between. Okay, so it is referring to the biggest rectangle possible. The subdivisions don't matter. It's the big one that really affects everything. The bigger that rectangle is, the bigger the subdivisions can be. So we need to find the big one. So we need to define some dimensions. And it doesn't matter what you call them. You can use A, B, C, what the letters are relevant. Okay, so I'm going to define the smaller pieces, the widths. Each of them has the same dimension. They're all x's, right? They are the same width. The long one, just call your length y if you want. The letters, again, don't matter. You can pick whatever you like. Now I know I have 800 meters in total. Everything highlighted in green has to make up that 800 meters. So this means that if I add up all the x's and I add up the y as well, it has to total 800 meters. Right there are all the dimensions I have. So again, we're going to solve for a variable. It's easier to solve for y here. So y is going to equal 800 minus 4x. Again, I know I'm talking about area, which is really, and I'll write this, length times width. Because I have multiple x's in here, length and width are going to be the most helpful. And if I think about my big rectangle, right, in red, there's my length and width of the large rectangle, not the individual pieces, because y is the length of the whole thing. Each little piece for the small subdivisions then would be y divided by 3 if I cut it into 3 equal parts. But I don't know that I'm cutting it into equal parts. I just know they're smaller sections. It doesn't tell me that they're equal. So I have to assume I'm looking for the big rectangle because I don't know that. Okay, so length and width are going to be x times y. Okay, that's what's getting multiplied together. We know what y is supposed to be in terms of x because we just solved for it. Replace them. So I know that my area function in terms of x is going to be x multiplied by 800 minus 4x. Again, you can distribute. So you get 800x minus 4x squared. Reverse the terms, and we're going to complete the square again. So negative 4x squared plus 800x. And again, I know this is a maximum because a is negative, right? It's negative 4, so it opens downwards if you were to graph it. So we're looking for our vertex, which is a maximum. Factor out that negative 4. So I get x squared minus 200x. And now I'm going to add in a number. If I take 200 and divide it by 2, right, 200 divided by 2 is 100, square it, and I get 10,000. So inside my set of brackets, I'm going to put in 10,000, remembering that there is a coefficient here of negative 4, so really the number I put into the brackets was negative 40,000. So I need to add 40,000 to the outside. Again, remember that it has to get distributed. Negative 4 multiplied by 10,000, I really put in negative 40,000. To counteract that, I have to add 40,000 to make my 0. Okay, so since I've got that sorted out, write it in your standard form. So negative 4x minus 100 squared plus 40,000. Look for your vertex next. Okay, determine that vertex, and it's going to be 100 as your x coordinate, 40,000 as your y coordinate. So that 100 is telling you what your input to your function was. In our case, we input the value of x, and what we get out of it is the area when we input x. So I know the maximum area is 40,000. The dimension of x is 100. Okay, that's what I know. I don't know what y is right now. That's the last remaining thing that we need to find. And again, I had a formula to do it. The very first thing we did is define what y is. So y is going to equal 800 minus 4 multiplied with x. We know x is 100 now. So I know the value of y is 400. Okay, 400 meters. And I know that x is also 100 meters. And I know it's meters because they said 800 meters in the question. So there we go. I have my dimensions. Again, I completed the square, found the vertex. Very, very similar types of problems. Context changes slightly, but really the same thing that we did with the last one. A different type of problem that you could see is a revenue problem, which deals with money. Now, if you think about what revenue is, right? Revenue is the total amount of money generated when you sell something. So it's the price that gets multiplied by the number sold, not counting the startup costs or anything that I have to subtract here. This isn't profit, this is all of the total money taken in. Okay, total altogether. So if I think about this, there's a computer software being sold. It's $20 a piece. 300 people are willing to buy it at that price. So right now, if I were to sell it for $20, multiply that by the 300 people that are willing to buy it, I will generate $6,000 in revenue. It seems like a decent chunk of money, but it might not be the best I could do. Right? What happens if I increase the price? Could I potentially make more? Now, if I increase that price by $5, there's 30 less people willing to buy it. So now if the price is $25, 300 people aren't going to buy it anymore, but 270 will, right? 30 less people. And you're going to see I'm going to actually generate more money than I did before. Well, what happens if the price is $30? And I'm going to sell it to 30 less people. So if I multiply this by 240 now, I'm still going to make more money than I did originally. So I have to find that sweet spot where I can make the most amount of money. I don't want to sit there and test out all of the cases. So there's a formula that I can use to build it, and it comes from this revenue thing we just wrote out. Okay, so determine the sale price that will generate the maximum revenue and the number of students who will buy it. So revenue, again, is equal to the price multiplied by the number that we sold. Now, we have to define a variable here. We're changing something. The one thing that we're allowed to change is the price, right? So I can define a variable that describes how many times I change the price. Right? Do I change it once? Do I change it twice? I don't know. That's what we're looking for. So let's call that variable x. Let's define x as being the number of price changes. If x is the number of price changes, well then I can say that revenue as a function in terms of x is going to be, well, the price. Originally, that price is $20. But if I increase the price, increase means a plus sign, by $5, well, I just did one price increase, but I have to account for all of them, so it should be 5 times x. So if x is 1, that's one price change, which means my new price is $25. If there are 2 price changes, that means x is 2, and it would be 20 plus 5 times 2, which is 10, which would mean my new price is 30. Okay, so this will account for all the price changes, but the number sold has to go the other way, because right now 300 people are willing to buy it. So if x is 0, well then it's my original case of 20 times 300, but 30 less people are willing to buy it per price change. So if x is 1, the price goes up by $5, but it also drops by 30 people. Okay, so there's my formula. Right there is my function for this. Now, it's in factored format, but what I can do is write it in a completed the square format, our vertex form, our standard form for this. In order to do that, I need to multiply all my terms out first and then complete the square. So if I start distributing things, 20 times 300, that'll get me my 6,000 like we talked about, minus 600x, plus 150x, and then the last term, minus 150x squared. If I combine some like terms, my revenue function, and I rearrange them, negative 150x squared, minus 450x plus 6,000. Okay, let me just make sure I got my terms right. I think I did. Yeah, okay. And then what we'll do is try to complete the square here. So what you're going to notice is the numbers just get a bit larger. Our context now is dealing with money, so our numbers can be a little bit bigger in terms of dollars. So we'll factor out a negative 150. And I could do it from all 3 terms. I can just do it from the first 2. It makes no difference. I believe that's 3. Yeah. X. That should be a positive. My sign should change to make that work out. Okay. So I'll leave my 6,000 outside. And now the number that I can use to complete my square here, did I do that right? 3, okay. 3 divided by 2 squared. As a fraction or a decimal, it doesn't matter. 9 over 4. I got a double. I don't know if I did this right. Hang on here. 20 and 30. It should be 600. Yes, negative. And that's 100 and 300 times 5. That's 150. Oh, that's why. 1,500. That's why it was a little off. Okay. That's why it did make sense to me. Okay. So let's fix this. So that should change. This should be 1,500. So we'll fix that up. And now when I collect my terms, I get 900x. Okay, so this is better, I believe. Okay, so now let's try this again. Our revenue in terms of x, factor out our negative 150, so x squared. Now 900 divided by 150 is equal to 6. That's better. So plus 6x. Nope, sorry, it's still minus 6x now. Okay. There we go. Now that when I take my middle term of that 6, divide it by 2 and square it, divide by 2 you get 3. 3 squared is 9. But again, like the other problems, I didn't just add in 9. there's a coefficient on the outside. What I put in there is negative 150 multiplied by 9. Really what I did is put in a negative 1350 to this. So I have to add 1350 to account for that. So if I combine my constants outside and write this in their standard form, we're going to have negative 150 x minus 3 squared plus 7,350. Again, you have it in completed square format. Look for the vertex. So my vertex here is 373.50. So I know that the number of price changes is x, right? So x equals to 3. That's the number of price changes. That y coordinate of my vertex, my revenue, when x is 3, is 73.50. That's the maximum revenue. Okay, the total amount of money generated if I increase the price 3 times. So let's go find out the new price. If original was 20 plus 5 times the number of increases, well, I know I increased it 3 times, so my new selling price is $35. Okay, 20 plus 15. The number of students willing to pay is represented by 300 minus 30x. In other words, it's 300 minus 30 times 3, which works out to be 210 students. Okay, so the maximum amount of money here is generated when you do $35 multiplied by 210. You'll get your 7,350. If you do the next one, well, that means the new price is $40, but you're only going to sell it to 180 people. You can see the price starts to drop again. Okay, so there is the maximum of $7,350. Okay, we'll do another one that's quite similar. Okay, you've got a restaurant that sells 2,000 wraps for $1.50. Through some research, they determined that for every 10-cent increase, they sell 100 less. What's the price? What's the revenue? Okay, so we'll set up our equation again. Revenue as a function of x is equal to price multiplied by the number sold. Let's again make x the number of price changes. So our revenue function in terms of x equals whatever the original price is, so $1.50, 1.50. We're increasing the price, we're told, by 10 cents each time, so plus 0.1x. That affects how many we sell. So originally I sell 2,000, and we're going to sell 100 less, so minus 100 for every price change. Okay, so there we go. So we'll do the same thing, expand. So 2,000 multiplied by 1.5, that's 3,000. So that's this term. And then 150 multiplied by 100x. And we're going to get 150, so minus 150x. Here, this will be minus 200x, I believe. Let me just double check, because we don't need to have what happened last time. Yeah, so plus 200, good thing I looked. Plus 200x, and then minus 10x squared. So if we rearrange and collect like terms again, we've got minus 10x squared plus 50x plus 3,000. Plus 3,000. So again, we'll complete the square. We'll factor out our minus 10. So we've got x squared minus 5x. Leave your 3,000 outside. Find the number that go inside, but you're going to end up with a fraction. 5 over 2 is 2.5. Squared is actually, 5 over 2 is 2.5, so we'll square that for 6.25. Now, it depends on where you are. Some people leave it as a fraction, some people put in it as a decimal. Decimal might be easier to interpret here in terms of money, so I'll put that in there. Now, again, remember the coefficient. So the number I have to actually add on the other side is 62.5. Okay, because I actually put in negative 62.5 into my equation. So I have to add it on the other side. So when you finalize your format here, negative 10, and I can get my brackets again by square rooting x squared for x, square root the number you put inside, so take the square root of 6.25 for 2.5. The sign that goes in between them is the sign of your x term, so negative, that gets squared, plus 3062.50. Find your vertex again. So 2.5 and then 3062.50. And again, the vertex is going to tell you your variable you defined for x, so our number of price changes. This is going to tell you your maximum revenue. Okay, so I know what the revenue is. In order to find the price, the new selling price represented by $1.50 plus 0.1 times x. Well, I know x is 2.5, so it's $1.50. This should be a plus sign, sorry. Plus 0.1 multiplied by 2.5, which is really $1.50 plus 25 cents for a new selling price of $1.75. Right, I added a quarter. I increased the price 2.5 times to get $1.75, and we found the maximum revenue already, $3,062.50. So this exact same question, set up your revenue in terms of price and the number of things you sell, complete the square, find the vertex, actually answer the question. Very, very similar. The one last thing we've got to talk about, the last type here, is a projectile question. So imagine something gets thrown or kicked. Soccer ball, football, you just throw a ball in the air, whatever. The height is given to you in terms of seconds by this equation, negative 4t squared plus 48t plus 3. Now, we're asked to use a graphing calculator to do this, so I can literally just graph this. Now, in my calculator, when I go to graph it, it will be in terms of x. So you can, the variable again is irrelevant, so height as a function of x is negative 4x squared plus 48x plus 3. Okay, so when you graph this, this is what it will look like in your calculator. So when y equals, so we'll do negative 4, x is next to alpha squared plus 48x plus 3, and then hit graph. You're probably not going to see a great picture here. So I know this opens downwards, so this is the left side of my parabola. So if I press the zoom button, zoom 0, or scroll to the bottom, it says zoom fit. Now it will basically just fit most of that graph on your screen so you can see it. So it gives us a good indication of where things are, and then we'll alter the window settings to actually see the whole thing. So I need to see the other 0 here. So if I hit window, my x maximum at 10 isn't enough, so I'm going to make it 15. Press graph to reevaluate if you can see it now. So I can, so that's good. It's still a little zoomed in on the bottom part, so we'll take some of that y minimum out. It goes all the way down to negative 877, so maybe let's make that negative 100. Make our picture a little bit easier to see. That's pretty good, actually. So let's leave it right there. Now, maybe let's make this so it's not having a rounded number, so let's make it 150 and make it nice. And what we can do is actually write the window settings. So maybe I'll write them at the bottom of the screen here. Actually, I'll zoom. We'll do like that. So here's the window settings. Window. So for x, we have a minimum of 10, negative 10, maximum of 15, a scale of 1. For y, your minimum is negative 100, maximum 150, scale of again 1. So there are the settings I used to generate this picture. So you can use them on your calculator if you like. And let's go find the height. So the height of the projectile 3 seconds after the launch. Well, if you remember, your variable is defined well, t is actually the time. In our graph on our calculator, we made x the time. So really, we need to make x equal to 3 seconds, and we'll find out what the height is. So if I hit second trace, the value, I want to hit option 1 here for value. My calculator will ask me for an x. So I'm just going to make x 3, hit enter, and then it tells me the height, 111 meters. So after 3 seconds, it's at 111 meters. I didn't have to do anything algebraic. B, find the maximum height. So really we're looking for the vertex. So second trace again for your calculate menu. I know it's a maximum, so option 4. And put your cursor on the left side of the maximum, hit enter. Move your cursor over to the right side of it, hit enter again, enter one more time. And there is your maximum value, your maximum height. Right? The vertex has coordinates of 6, 147. So your max height is 147 meters. If we were going to do this by hand, we would have to complete the square to find it. How many seconds after the launch is that reached? Well, the vertex tells me 2 variables. The x coordinate is time, the y coordinate is height. So I know now that x has to be 6 seconds. What is the height of the projectile at launch? Well, if I'm launching it, that's when x should be 0. The original, the time 0 of this to see where it happened. So really what you're looking for is the y-intercept. So again, you can make a value for x, but make it 0, and you'll see that the initial height is 3. So this is a question asking you for the y-intercept. So make x equal to 0, and you'll see that y is 3. So we don't start on ground level, we're starting 3 meters above the ground. Maybe we're on a platform or something, maybe it's raised, we don't know. Determine an appropriate domain and range for the scenario. Now domain talks about all the x values. So if I set this up, it's the set of x values given the restriction. Well, there's certain x values that I have to exclude here. X means time. I can't have a negative for time. The smallest it could be is 0. Okay, so x has to be greater than or equal to 0, or x has to be less than or equal to 12, because, well, if it takes 6 seconds to get to the maximum height, physics tells me it has to take 6 seconds to come back down. So 12 is going to actually be my other 0 here. And if you want to calculate it, you can. Option 2 is 0. Scroll all the way over to the left. And I'll get my cursor close there. So there we go. Enter. Scroll underneath it. Enter again. Enter one more time. And it will tell you it's 12.06 something, but my y is really not directly on 0. It's very, very small, so I can round both of those. For y is 0, x is 12. So I know this situation occurs from 0 to 12 seconds, but other than that, x can be any real number in between those two. So there's my domain, and for y, it's the set of y values given the restriction that, again, the minimum height is 0. It hits the ground, so y has to be greater than 0, but it has to be less than or equal to my maximum value of 147. Right, that was from my vertex. If that's the maximum, it can't go bigger than that. Okay, so there's my y value there. We've answered all of them, and again, we could have done this by hand as well, by completing the square, plugging in values for x, finding the vertex. All of those things are still true. Okay, but using the calculator is also helpful. If this is a multiple choice numeric response, where you don't have to show your work, that was pretty quick for us to find each of those things. Okay, so that wraps up our lesson on quadratics, our unit on quadratics, with the longest video I think we've ever made, just under 50 minutes. But it does show you a variety of applications and what we can do with quadratics. Okay, so that wraps up our unit. The next one will be on radicals and absolute values. So you'll see those videos as well. And again, all the links you'll need are in the description. So I hope that is helpful. And until next time, enjoy the rest of your day, whatever that looks like for you. Take care. We'll see you next time.